Hi Rockridge, this is Mrs. Berger, and this is Probability and Statistics, Unit 3, Day 1. There are 2 days of notes. Today we'll be going through Day 1 of notes. This unit is on 2 variable quantitative data, so bivariate data. Instead of analyzing one set of data like student age or student height, we'll be looking at 2 different sets of data, so maybe as a student grows in age, they grow in height as well. So we'll see how one variable affects the other, okay? And so we're starting out in the textbook on lesson 2.1. If you've got your textbook handy or your online textbook, that would be good. And also make sure that you have your graphing calculator, your TI calculator handy so you can remember how to enter data and analyze data on the calculator. So let's get started. Let's take a look at the first thing that we're tasked with here, and that is to compare and contrast response variables and explanatory variables. So the main difference here is that a response variable, as you can probably infer, a response variable is one that measures outcome. Okay. It's typically on the y-axis, or almost always on the y-axis, and it measures output. On the contrary, if you want to talk about explanatory variables, those are the variables that predict or explain the change in the response variable that's on the x-axis, and that's of course input. So those are the differences. Make sure that you understand as you read a scenario which one of these is my response variable and which one of these is causing the response variable or the explanatory variable. Alright, so let's take a look at another vocabulary word here. How do you know if there is association between 2 variables? If you were in class before this lesson was given, we did a little exercise where you saw how good a dinner partner you and your partner would be, how much your likes and dislikes of foods lined up, and you'd see if there was an association between your likes or not an association between your likes. So that association technically is if knowing the value of one variable helps you predict the value of the other variable. That means there's association. So if knowing the input helps you predict the output, then there's association between those 2 variables. If knowing the input doesn't really tell you anything about how the output's going to be, then there's no association between the 2 variables. Okay? Alright, so in your book, we're moving to lesson 2.2 now, if you're following along, and we're taking a look at scatter plots. So in scatter plots, make sure that I'm sure you've seen scatter plots for years now, but in a scatter plot of data, the explanatory variable is placed on the horizontal or x-axis, and the response variable is placed on the vertical or y-axis. Whenever we talk about a scatter plot, we have to talk about 4 things, right? Remember histograms were our univariate data, our one variable data. We had to talk about SOCs, shape, outliers, center, and spread. Well, now with scatter plots, with bivariate data, we have another 4 things we want to talk about. We always want to talk about direction, form, strength, and outliers. Okay? Now, what are the possible examples? So these are the characteristics and some examples. For direction, you really only have 3 choices. You either have positive direction, negative direction, or none. There's no direction to the data. For form, in this class, we're going to keep it simple. We're either going to say the form is linear or nonlinear. If you take AP statistics or statistics in college, we'll get a little fancier with the nonlinear. We'll get more granular on that. But in this class, in probability and statistics, we'll just say the form is either linear or nonlinear. For strength, You really only need to tell me one of three things. Is it weak? Is it moderate? Or is it strong? Some folks like to maybe create little in-between, so it's weak to moderate or moderately strong, and that's fine. We'll probably agree with anything that you justify with your look at the data, but these are really the only three that I need to see. It's either weak, it's moderate, or it's strong. And then of course outliers, and we all understand what outliers are from a conceptual standpoint, but we need to make sure that we understand that technically outliers are points that are outside the pattern, the overall pattern of the data. If the data is following a pattern and there are certain points that aren't following that pattern, that's an outlier. Now, I want to switch over to the calculator real quick just to help you remember. And in the book, it tells you the steps for entering the data and analyzing the scatter plots as well. But let me remind you, on your calculator, remember you need to hit the Stat button to enter data. You'll hit Edit. And of course, for bivariate data, you need data in List 1 and List 2. I just threw some random numbers in here. If you'd like to choose other numbers, that's fine. We're just playing around with it right now. So Stat, Edit, make sure you put your data into List 1 and List 2, and make sure that they match as far as heights of the tables. Every input needs to have an output in List 2. Now, make sure that second y equals has stat plots turned on. You can either turn one of them on or all of them on, but make sure that they're on, otherwise you won't be able to see your scatter plot. And then to see your scatter plot, you need to zoom 9. Zoom 9 takes you out of the standard zoom window into the window that includes all of your data. So zoom 9 if you want to see the data that you input into Stat Edit. Okay? So as a refresher, those steps were Stat, Edit, data into List 1 and List 2, and then second y equals, turn stat plots on, and then zoom 9 to see the data. This will give you your scatter plot. If I can spell scatter plot, sorry about that. That will give you your scatter plot. And always look at your scatter plot before making any determinations. That's going to give you an understanding of what the data looks like. Alright, now don't forget these 4 characteristics. We're going to need those as we look at some of the example questions. So let's go ahead and look at example question 10. Example question 10 in section 2.2. Let me pull it up for you here. Take a moment and read the question, read the data, and try to answer in your head. Maybe pause the video, answer in your head before I reveal the answers. Alright, hopefully you paused the video and read through the question and immediately thought to yourself, wait a second, they asked me to describe the relationship of this data of IQ score and GPA. They must want me to address those 4 different things: direction, form, strength, and outliers. So hopefully with direction you saw that it was a positive relationship. We can see it moving up and to the right, so it's a positive direction. I want to add a little bonus notation here for you. If I was to ask you to give me the direction and explain what that means in context, here's what that would mean. If the direction of that data is positive, that means the higher the IQ scores, means higher GPAs. Okay, so make sure you can do that in the context of your problem. Alright, now form. If we take a look at the form of the data, it certainly looks linear. And from a strength perspective, if I imagine a line of best fit that follows along here, the data really does hug close to that line. There is a little bit out here, but for the most part it's got a moderate form here. Obviously not as strong as a line through my example data here. That would be extremely strong because that's a nice straight line. But for our data here, I would say that the strength of that is moderate. So my form is linear, my strength is moderate, And hopefully you saw, as you were reading this during the pause, hopefully you saw a couple of outliers. You saw maybe this outlier, and hopefully you saw these two outliers as well. Whenever we have you write outliers, we want to make sure that you call them out with their coordinates, okay? So 2 students are below the trend or the pattern. Those students are at 102 IQ with a GPA of 0.7 and 109 at a GPA of 1.9. And then there's one student above the pattern, and that student is at 72 IQ and a 7.3 GPA. Okay? So that's how you would address describing the relationship. Okay, let's flip to question 20. Question 20 talks about lean body mass versus metabolic rate and talks about the difference between women and men. The men are in the orange dots and the females are in the purple dots. So our first question is, does the same overall pattern hold for both women and men? And hopefully you're looking at this and you're seeing that the overall pattern, as lean body mass increases, metabolic rate increases. That's true for women. And as lean body mass increases, metabolic rate increases for men as well. That's true for men as well. So the answer to this is yes, the same pattern holds, the same direction. So we would say yes for both. There is a strong positive linear association between lean body mass and metabolic rate. Okay, that's the answer to the first question. Now let's look at the second question. What difference between the sexes do you see in the graph? So what is different between the purple dots and the orange dots? Think about that for a moment. And hopefully you see that the relationship is not quite as strong for men as for women. If you imagine a line of best fit going through the men, the data is a little bit weaker than if you look at for the women. The women is closer to a line of best fit. It's closer correlated. It's more strongly correlated or associated. Okay? So for this, the relationship between, certainly the relationship I'm talking about is between lean body mass and metabolic rate. The relationship is not as strong for men as women. You also saw that these orange dots are higher than the purple ones, so we can address that by saying men tend to have higher lean body mass and metabolic rates than women. Okay? So that's the type of question you would answer on a quiz or test. Make sure that you understand how to address direction, form, strength, and outliers, and that you can compare 2 sets of data. Let's move to lesson 2.3 in the book and talk about correlation. Correlation is sort of a shorthand for 2 of those things we talk about. Correlation talks about strength and direction in a linear relationship between 2 quantitative variables. So if we would need to talk about direction, form, strength, and outliers, you could cover the discussion of strength and direction just by addressing correlation. By saying correlation has such and such a value, you are explaining the strength and direction with that value. A correlation, or R, is a value between -1 and 1. If the data is trending downward, if you can think of a negative slope, if it's trending downward, R is a negative value. If the data is trending upward, that R, that correlation, is a positive value. If there's no correlation between the two variables, R is 0. So let's take a look at the lesson app 2.3 on page 117 and see if we can answer questions 1 and 2. As we read this question, we want to understand what's going on with this data here, plotted on the chart, of the different countries around the world. The explanatory variable on this chart, on this scatter plot, is chocolate consumption in kilograms per year per person. And the response variable, Nobel laureates per 10 million people, is on the y-axis. And as you can see, it appears that there is a positive linear association between the data, with Switzerland up here on the top right. And our first question is, if there was a line of best fit calculated for this, and it had an R value, a correlation of 0.791, how do we interpret that? Let's interpret that. Now, put aside whether or not you believe that eating more chocolate causes countries to get more Nobel laureates. Put that aside and just look at the correlation. This is a fact. There is a correlation between chocolate eating and Nobel laureates, and that correlation has an R value of 0.791. We need to interpret that. So to interpret that R value, here's what we say. A correlation of 0.791 indicates a moderately strong positive relationship between chocolate consumption and number of Nobel Prizes. Okay? Now, that's just correlation. Let's look at our second question. If people in the US started eating more chocolate, can we expect more Nobel Prizes to be awarded to the residents of the United States? Why or why not? Now, your common sense is probably kicking in right here. Obviously, there's probably no correlation, right? Probably not. And the explanation for that is that the variables are correlated, but that's not the same as causation. You're probably saying this before I write it, right? That's not the same as causation. What's probably going on? What did we learn about during experiments? It's more likely that there are other variables like what? Like income, education, etc. Right? There are other things going on in those countries that are winning those Nobel Prizes besides eating chocolate. Okay? So you can absolutely address correlation and explain what the correlation says about the data, but you're not necessarily proving causation. You would need to run an experiment, a very controlled experiment, to prove causation. Okay? All right, let's go ahead and take a look at exercise 18. Question 18 asks, if you have these different scenarios here, number of pull-ups a person can do and number of push-ups, number of pull-ups a person can do and the number of sit-ups they can do, and the number of pull-ups a person can do and their weight. 3 of these situations have had their correlations calculated. And those correlations are listed here. One of those scenarios has a correlation of 0.9, one of them has a correlation of negative 0.5, and the other has a correlation of 0.3. We need to figure out which correlation goes with which relationship. So I've set that up here. We've got to figure out what goes with what. And certainly you can argue several different ways on some of these. Let me talk about how the book explains the correlations and the matching. If you have a different idea of what this means, then certainly justify it on your quiz or test and you'll probably get full credit, okay? But let's follow along with the book's reasoning on these. Correlation between number of pull-ups and number of push-ups. Is that a negative correlation, a positive correlation? It's probably a positive correlation. And if we were to compare that with the others, pull-ups and push-ups, pull-ups and sit-ups, since pull-ups and push-ups both exercise the arms, the book explains, well, that would mean that there's a strong correlation. A positive strong correlation, 0.9. Because they both work out the arms. If you are good at pull-ups, you're probably good at push-ups. And then the book says, well, if you're good at pull-ups and sit-ups, it's still exercise, but one of them does the arms and one of them does the abs. So there's probably a little bit less of a positive correlation, but if you're in shape, there's probably a positive correlation. It's just not as strong as the correlation between the number of pull-ups and number of push-ups you can do. So that, of course, leaves the number of pull-ups and a person's weight as a negative correlation, meaning the more you weigh, the fewer pull-ups you can probably do. Now, those of you that are athletes or that work out a lot can probably argue differently and can probably have a lot of experience with the data that you have, could probably argue one way or the other. As long as you explain your reasoning for your arguments, you'll probably get full credit, okay? But that's what a type of scenario would be on a quiz or test. Which of the following R values matches most appropriately with these scenarios, okay? All right, moving to lesson 2.4. If you were to review the lesson material on 2.4, the first question I would want you to understand is, what types of data points can have a significant impact on the correlation between two variables? Now, lesson 2.4 has a lot of words and a lot of examples and a lot of data, but if you think about it, what types of data points will have a significant impact on whether or not two variables are strongly correlated or weakly correlated? The types of data points that have that impact are outliers, and we're going to look at several examples of how these outliers can have an impact on the correlation between those variables. So if you go to lesson 2.4's exercises, we're going to take a look at exercise 8 first. Exercise 8 talks about nutritious grains, and as we look at this data, a lot of different grains and flours are plotted on this scatter plot, and the explanatory variable is carbohydrates and the response variable is protein. So depending on how much carbohydrates we have, you can predict how much protein there is. Now, both nutrients are measured in grams per cup, and the correlation that they've calculated for this data is a positive 0.545. The question we're first asked is, what would happen to the correlation of the carbohydrates if the carbohydrates were plotted on the vertical axis and the protein was plotted on the horizontal axis? This is a favorite question of statistics teachers. We love trying to get you on this one, okay? If you were to switch the axes, you need to understand that the correlation is going to remain the same. Correlation does not distinguish between explanatory and response variables. Okay, so if you switched carbohydrates to the y-axis and protein to the x, the correlation would not change. So for part A, correlation would remain the same. Correlation doesn't distinguish between explanatory and response variables. And I would star this note for yourself because it's an important one. It may pop up in a multiple choice question. Part B, what would happen to the correlation if carbs was measured in ounces per cup instead of grams per cup? So if we changed the unit of measure on carbs, but not on protein, would the correlation change? I'm not talking about the scatter plot itself. I'm talking about the correlation of the data. I'm certainly, by giving you these extra comments, leading you down a path, right? I'm leading you, hopefully, to think she must be implying correlation would remain the same again, and that's exactly what I'm saying. The correlation would remain the same. Correlation doesn't change when units change. The strength and direction of the data stays the same. The strength and direction stays the same, regardless of units and regardless of who's on the X and who's on the Y. So I would star that as well. Remember, correlation is just strength and direction. All right, let's go ahead and take a look at question 10. Should travelers avoid flying airlines that have had crashes in the past? So this particular question has a bunch of data collected about the deaths per trillion seat miles, that's the explanatory variable, and the between 1985 and 1999, and the deaths per trillion seat miles from 2000 to 2014. So go ahead and take a look at that data. All of these are different airlines, and this data point right here is Kenya Airways. So how does the point highlighted in red affect the correlation between deaths in the previous period and the recent deaths? Hopefully you've paused the video and thought about the problem for a little bit. Let's first think about the green dots without the red one. What kind of association do we have there? If we thought about how the data is trending and how weak or strong it is, hopefully you see that any particular line would be almost flat. So if there was deaths in between the 80s and the 90s, it doesn't necessarily mean there's going to be deaths in the 2000s. So previous deaths on the airlines, or crashes, previous deaths on the airlines doesn't really strongly predict whether there will be deaths on the airlines later. So we'll summarize all that we just waved our pointer around about. We're going to summarize that by saying the green points have weak positive association, now let's look at the red dot. The red point would take this weak positive association, and if you were to add that to the data mix, you would have to incorporate it in here, and you'd almost have to maybe either drag it to 0 or even drag it to negative. There might even be a negative association. If there were deaths in the past, there's really not going, that's less of a predictor. So Kenya Airways takes this weak positive and turns it closer to 0 and almost negative. So that's the effect of that outlier. The red point drags the correlation closer to 0 and possibly negative. Okay? So the more deaths that you had in a previous year means you have fewer deaths in the later years. Alright, let's look at another example here. Let's look at question 12. Brainy or brawny. These are the body weights of different mammals plotted against the brain weights of those mammals. And you'll see most of the data is down here. Here's human and dolphin. Most of the data is down here. And you can see a positive association, hopefully. And we want to know what effect the elephant has on this correlation. So if you think about, imagine the elephant dot wasn't there. Think about all the data points down here. Think about how associated they are. And then imagine the elephant is popped up right there. What does that do to the correlation? Does it strengthen it? Does it weaken it? Does it flip it directions like it did the Kenya Airways? Hopefully you came to the conclusion that the other points do show a positive association, and the elephant pulls the correlation more positive and closer to 1. It just really strengthens this relationship. Kind of gives it a place to go, right? Instead of hovering back and forth across a potential line of best fit, this elephant drags it more positive. So the other points show positive association, the elephant pulls the correlation more positive and closer to 1. All right? Now, let's take a look at example 14. Finding the mistake. This is another statistics teacher favorite type of question. So we don't have any data to look at here. We just have these statements. Someone has done a bunch of work and they're declaring these things. They're declaring A and then they're declaring B. And we have to explain what is wrong. What did they say wrong in this sentence? The correlation between the distance traveled by a hiker and the time spent hiking is R equals 0.9 meters per second. What is wrong? Somewhere in this statement, something is wrong. Think about that for a moment. Pause the video if you need to. Think about it. And hopefully you noticed in the past we have never had units on R. R never has units. You say correlation has a value. You don't say it has a value with units. So that's what was incorrect about A. Correlation R has no units. And you may want to star this one. It's certainly a favorite statistics teacher popular question, either multiple choice or short answer. Let's look at B and see what they did wrong. There is a correlation of 0.54 between the position a football player plays and his weight. Pause the video and think about the potential answer to that. What's wrong with that statement? Hopefully you pause the video to think about that for a minute. And you realize that the position a football player plays, quarterback, cornerback, running back, lineman, that's not something you can plot on an axis, right? That's not a quantitative variable. That's a categorical variable. And you can't calculate correlation, or R, with a categorical variable. So that's what's wrong with B. Position is a categorical variable. R is only for 2 quantitative variables. Okay? Alright, that's the end of this lesson. Go ahead and take a break, try your homework. I think up through questions 3 or 4 go with this lesson, and then go ahead and take a look at the other video if you need to for day 2 notes.